So this is part 2 of our introduction to focus degradation kinetics, and as I promised, we're now going to start looking at specific issues when you start adding metabolites into your kinetic assessments. Again, just an outline of the presentation. I'll start with a few words about pathways and how you put degradation schemes and metabolism pathways into your kinetic models. I'll introduce the concept of formation fractions, which is a really important additional parameter that you will need to understand if you're going to implement different degradation schemes in a kinetic assessment. A few words on visual assessment. The tools for assessing the visual fit are the same as we've already talked about for parent, but I'll just say a few words about some specific things that you need to be aware of when you're looking at visual fits for metabolites. Then we'll talk about how you go about choosing or selecting modeling endpoints for metabolites. Similarly, the kind of decisions that you would make for trigger or persistence endpoints for metabolites. And then because things get a little bit more complicated with metabolites, you often find yourself having to make more case-by-case decisions. So we'll go through a few of those case-by-case options at the end of this section. And as I said earlier, that will then move on to hands-on exercise part 2, which again, building and fitting models in Model Maker with metabolites. Okay. Just a reminder that for metabolites that are applied as test substance at the start of a study, so if you've got a metabolite dosed rate of degradation study, for example, the kinetics should be derived following the recommendations as per parent substances. So you can follow chapter 7 of Focus Kinetics, even if it's a metabolite, but if your metabolite is applied as your starting material, then treat it like a parent. If you get subsequent metabolites formed, so if you've got a rate of degradation study on a primary metabolite, but you know there are also secondary metabolites, then just remember the limitations of those biphasic workarounds. So things like the FOMC DT90 divided by 3.32, we said that was a limitation if it was used for a parent substance. It's still a limitation if you use that for an intermediate metabolite. Okay. For the rest of this presentation, we'll focus on metabolites that are formed in situ in any study. And all of this is covered by chapter 8 of Focus. So in terms of pathways, the conceptual model, which remember is just the thing that you build in the software package. So the things that you were building in Model Maker, the things that you will build in Cake later on today, that conceptual model must reflect your actual degradation or dissipation pathway. If you don't build the right conceptual model, then you won't get a good fit between your model and your experimental data. Okay? When we build pathways, we retain those flows to a sink initially, and they can be included to cover formation of other metabolites. They might be minor metabolites. They might be ones that you identify or ones that you don't identify. That flow to a sink can also cover formation of non-extractable residues and CO2. So in our Model Maker fits this morning, you just had a parent going to a sink. Okay. In this conceptual model, we've got a primary metabolite that we've added in. But when I say the flows to sink are included initially, it's this flow that is retained. Okay. So keep that flow to a sink and only remove it if you subsequently found that that flow is not significant. Okay. This is just an example of the same data set fitted with two different conceptual models. So on the left, we have a parent to a metabolite with no flow to a sink, and on the right, we have a conceptual model where we've retained that flow to a sink. And the only thing to notice really is that without the flow to the sink, we get a relatively poor fit of the parent to the initial amount. Metabolite DC50, 16 days. When we include the flow to the sink, we get a much better fit for our parent model, and it actually has quite a big impact on the metabolite DT50. The metabolite DT50 with that flow to a sink is twice as high as it was without it. Okay, so you may not understand the importance of this at this point, but when we're thinking about pathways and the conceptual model, just think that the conceptual model must reflect your degradation scheme, okay? Because if it doesn't, all the software will do is try and find the best combination of parameters to minimize your residual sum of squares, okay? So it's just a mathematical process when you hit the optimize button, okay? But if you give it the incorrect pathway, you might get parameters that are not actually correct. Also. Formation fractions, okay? So the formation fraction is the fraction of the amount of precursor substance that is transformed into a degradation product. Okay, so in our conceptual model, again, we've got a parent just to a primary metabolite. That formation fraction parameter comes in here, and it determines the fraction of this precursor that is transformed to our degradation product. So it's just an extra parameter that we use to start to determine how much flow goes from parent to metabolite and how much flow goes from parent to sink. Okay. For radiolabeled studies, which are most typically the studies that we have when we're thinking about route of degradation studies, not always, but most of the time they're radiolabeled, that formation fraction will be expressed as a molar fraction. So it's how many moles or how many molecules, if you like, of parent will degrade via one flow and how many moles will degrade via alternative flow routes, if you like. Formation fraction can be included as a parameter in the fitting procedure, and that's the approach that we will take you through in our second hands-on workshop. Or for combinations of single first order reactions, you can actually calculate your formation fraction from separate rate constants. And I'll show you that briefly, but to keep it simple, we'll be thinking mostly about formation fraction as a dedicated new parameter that we need to define and include to describe these conceptual models. And this is the conceptual model with that formation fraction included. So if you think back to what we were doing this morning, it was just a parent going to a sink, okay? Now we've included this primary metabolite, but we still have our standard parameters for the degradation of our parent according to single first order kinetics. So we still have this Kp rate constant parameter, but what we've done here is we've added in our new parameter, our formation fraction for metabolite, that tells us what fraction of parent is degraded to the metabolite. Because the sum of formation fractions from a single substance is almost always 1, okay? Sum of formation fractions from one substance should be 1. To maintain that rule, the flow from the parent to the sink has to be our rate constant multiplied by 1 minus formation fraction metabolite. So the flows, the formation fractions from the parent in that conceptual model, the formation fractions will add up to 1 because it's FFM plus 1 minus FFM. And even my maths in the afternoon tells me that equals 1, okay? For the metabolite, we also need to define its own degradation rate parameters. And in an SFO model, we'll have a second first order rate constant, Km, to describe the rate constant for how the metabolite degrades as well. Yeah. So it's starting to get a little bit more complicated now. Not only have we got formation fractions to tell us how much of the parent degrades via those different flow pathways, we also need to have rate constants that describe how quickly our metabolite degrades, because the metabolite is not going to degrade at the same speed as the parent. Okay. We have the differential equations on here. The one for the parent is the same as you've used already. The differential equation for a metabolite, we have like a formation phase, so this is how it's formed via this flow into that compartment. So it's formed by a rate that's determined by the parent rate constant, the amount in that parent compartment, and this formation fraction. And then we have a negative flow as the metabolite degrades, and that is very similar, or it's the same as the single first order differential equation. It's just that rate constant multiplied by whatever's in that metabolite compartment. Okay. A couple of extra points to point out. Metabolite formation fraction is not the same as the maximum observed in your study. So when you have a route of degradation study and you'll see your metabolite being formed, you'll have some indication of what the maximum amount of metabolite formed is. That is not the formation fraction. Okay, the formation fraction comes from a kinetic analysis like this. Formation fraction is actually always greater than the maximum observed, and I'll explain that in a few moments' time. For PEC modelling, environmental modelling, you need to think whether you need a formation fraction or whether you could use the maximum observed. Okay. Generally, if you're thinking about groundwater modelling, where you are sequentially modelling the degradation of a parent to a metabolite, then absolutely you need to use formation fraction, and you shouldn't use maximum observed in that kind of sequential model. If you have other types of PEC modelling where there isn't that sequential modelling of parent to metabolite, then it might be more appropriate to use maximum observed, but I'll come back to that again because we have specific guidance for biocides that handle that situation. So although that might look a little bit more complicated, hopefully as you work through example 2, you'll start to build on the knowledge that you gained in the first workshop, and some of these concepts will not be so complicated for you when you start to see what you're doing when you add that extra compartment for the metabolite. Okay. I'm not going to spend any time on this, but this is just the same kind of conceptual model, but rather than using formation fractions, it now uses individual rate constants. So we have an individual rate constant that determines the flow from parent to sink with a first order rate constant KPS, and then we have a separate rate constant that describes the flow from the parent to the metabolite compartment, and that first order rate constant in this example is KPM. And just to say that the metabolite formation fraction in this conceptual model is just this flow in divided by the sum of flows out of the parent. Okay, so I said that you could define formation fraction based on single first order rate constants or formation fractions. That's the version with rate constants, but we're going to stick with our formation fraction approach as a dedicated parameter throughout the rest of the course. So just one thing to say, use sensible names for things like rate constants and formation fractions once you start to build conceptual models in Model Maker, because very quickly you will start to lose track of what KPM means if you've got multiple metabolites. Okay, so read the guidance. Just a few words on visual assessments, really focusing on what's different about a visual assessment for a metabolite. Okay, so unlike parent assessments where we just start with the maximum amount of mass, 100% for example, and it degrades, for metabolites we have different phases, if you like. So we have a formation phase when the metabolite is being formed rapidly as the parent precursor degrades. If you're lucky with your data, you will describe this plateau or peak level, and then you'll have this decline phase towards the end of the study. And each of those phases can be defined by thinking about the flows in and out of the metabolite. Okay, so in our metabolite conceptual model, we've got a flow in and we've got a flow out. So when, during the formation phase, the flows in, determined by this part of the equation, are greater than the flows out, which are determined by this, the metabolite degradation part of the equation. At that peak plateau level, in theory, the rate of formation and the rate of degradation are the same. So the flows in and out of that compartment are balanced. And then towards the end, during the decline phase, the rate of flow out of that metabolite compartment is greater than the flow in. Okay. And of course, the rate flowing into the metabolite compartment does slow down as the source of it, the parent itself, degrades. So when you get down here, there is no more parent forming metabolite, okay? So it changes over time, so it becomes a bit more complicated. This graph was created with a single first order model. So parent degrades, single first order, metabolite degrades, single first order, and we set the formation fraction to 1. Okay, so when I said the formation fraction does not equal the maximum observed, you can see that's true because the formation fraction is 1, 100% is formed, but the peak is only around 60%. And the reason that formation fraction and peak are not the same is because during this formation phase, the metabolite is still degrading. Okay, so as it's being formed, it's also degrading. So you never get peak observed to be the same as formation fraction. These are just a couple of examples of what you will quite typically see when you start looking at metabolite fits. So we've got a couple of different studies here, if you like. And the slide asks, well, which metabolite degraded faster in this example? And if you don't look at the answers, you might think that example 1 is degrading more quickly because you've got a clear kind of decline phase within the study, where in example 2 on the right, you're not really describing much of a decline phase. In actual fact, in both these examples, the metabolite DT50 is the same. And the reason they don't look, the reason that metabolites don't look the same is because the shape of the metabolite is also determined by that formation from parent. So the rate of degradation of the parent will also determine, to a great extent, the shape of your metabolite curve. So it's not possible to just look at metabolite patterns on their own and know what the DT50 is. You have to have a good description and a good understanding of the rate of degradation of the parent as well in order to be able to actually kinetically derive degradation rates from metabolites. Again, both of these examples were created with SFO models with a formation fraction of 1. So you can see even there, even with the same metabolite degradation rate, you get quite different peak levels of occurrence. So example 1 peaking at 60%, example 2 peaking at half that amount. And that's because that formation phase is longer in example 2 because the parent degraded more slowly. Okay, so there's just things to be aware of that are different when you're thinking about visual assessments. Think about those: the formation phase, the peak, and if you're lucky, the decline phase. Unfortunately, we're not always lucky, and we don't always have decline phases. Okay, so this is just a couple, or it's an example of exactly the same data. Both of those graphs are the same data sets fitted with, with 2 different combinations of optimized parameters. Okay, and visually and statistically, the fits look pretty similar. I think you wouldn't really be able to easily tell or differentiate between those 2 fits. Chi-squares are all pretty low. Everything's looking good. But just to point out that on the left, the metabolite DT50 is 77 days. On the right, the metabolite DT50 is 280 days. So it's really hard when you don't have a decline phase. That's something else to really look out for. One of the reasons that happens is because metabolite DT50 and formation fraction often are very highly correlated. And I think we talked this morning about when you have those parameters that are highly correlated, small changes in one parameter within the fitting software can be compensated for by changes in the other parameter. So in this case, a small change in formation fraction, for example, from 0.85 to 0.65 is compensated for by quite big changes in that example, but big changes in the metabolite degradation rate. Okay. Another thing to look out for with metabolites is the importance of the parent fit. Again, top and bottom is the same data fitted with two different models. So on the top we've got the SFO, and on the right the SFO metabolite fit. On the bottom we've got the default parent SFO metabolite. If you ignore this one for a moment, the SFO fit to the parent is not terrible, I would say. If you look at the visual fit, it's okay, maybe. Chi-squared is 5.2, and it's possible that when you look at how good the metabolite fit is, you might be quite tempted to accept that as an acceptable fit. With the SFO model, the metabolite DT50 is 66 days. But if you chose to reject the SFO parent fit, if you thought that wasn't quite good enough, despite the chi-squared of only 5.2, if you said, no, I don't like that fit, I'm going to fit default to it, when you fit the default fit, you obviously get a much better fit to the parent decline. The metabolite fit actually looks very similar. I think you would agree. There's hardly any difference between the metabolite fit, except to say that in this example, the metabolite DT50 is now over 1,000 days, whereas previously, with almost the same visual fit, the metabolite DT50 was only 66 days. So again, really important that you have a good description of the parent, because that parent fit also determines, to a great extent, your metabolite. Okay. One thing to look out for, if your formation fraction ever optimizes to 1, as it does in this case, sometimes the software can optimize that formation fraction to 1 because it's desperately trying to form as much metabolite as it can, because actually this isn't quite the right kinetic model. So in this phase, your SFO fit isn't quite forming enough metabolite quickly enough, so the model mathematically optimizes your formation fraction to 1. But when you fit the right kinetic model, or a better kinetic model, on the lower figure with default, you can see that the formation fraction is now fitted to a value less than 1. But as I said, the metabolite DT50 is very significantly affected, and we'll come on soon to explain what you can do in those situations. Okay. So just be aware of those special cases, the importance of describing the formation, peak and decline. Be aware when you haven't got that decline phase, you need to be really, really careful, and also be really careful on the parent fit. So for modeling parameters, we need to understand both the formation and degradation phase. Okay, so for the formation rate parameters, that's the degradation rate of the precursor. For a primary metabolite, the precursor will be your parent substance. And you need the formation fraction to tell you what fraction of the precursor is degraded via the metabolite. And you also need to understand the degradation rate parameters, and that will be the degradation rate parameters of the metabolite. Okay. So to estimate the parameters, you need to identify the appropriate kinetic model for the precursor. So for the parent, you need to decide whether that can be adequately described by a single first order or a biphasic model. Generally, we think that an appropriate description, at least up to 10% of the initial amount, is necessary. Okay, so if you get a reasonable fit up to 10% of the initial amount, so up to the DT90 of the precursor, that will also cover 90% of the formation of the metabolite. Okay, so by the time your parent has degraded to 10%, you'll have formed 90% of your metabolite. Okay, so if you can get a decent description, at least up to that 10% point, that might be good enough for your metabolite, and the last 10% is less critical. If you describe 90% of it, that might be enough. Okay. And then you also need to decide, make that decision on the appropriate kinetic model for the degradation of the metabolite. Luckily, single first order is nearly always sufficient for metabolites, even if the substance actually degrades via a biphasic kinetic model. And that's because the shape of the metabolite curve is influenced by both its formation, which is determined by the degradation rate parameters of the precursor, as well as its own degradation. Okay, So the shape of that metabolite, as you saw in some of those earlier examples, it's also determined by the precursor. So very often, single first order is good enough for metabolites, which is good news. I mentioned this morning advantages of DFOP modeling, and Julia asked a question about how to combine SFO, DFOP, hockey stick. I said that the DFOP rate parameters K1, K2 can be combined with SFO to derive average input parameters that are suitable for use in exposure models, like focused groundwater. The biphasic workarounds, those K2 rate constants or FOMC DT90 type approaches, for the parent are not necessarily going to be conservative for metabolites. So conservatively slowing down your parent degradation might adversely affect your metabolite exposure assessment, okay? So where a biphasic model is needed to describe the parent decline, DFOP is usually the best choice. So the ability to combine DFOP and SFO allows the derivation of fast and slow parent degradation rates, okay? And then you can test which gives the worst case for the metabolite. So on the right, we have a mixed database of experiments, soils, if you like, fitted with combinations of DFOP and SFO kinetics. So you can combine your fast phase K1 DT50s with SFO to derive a fast geometric mean value, 12.9 in this case. And you can also combine your slow phase K2 rate constants with the SFO DT50s to derive a slow phase geomean, which is 60.7. And the simplest thing to do is actually run your models twice with fast parent and then slow parent, and pick whichever gives you the worst exposure values for the metabolites. Or, as I said, DFOP can also be implemented in emission scenario document type ECA Excel calculation sheets or the focus models. If you were trying to implement that type of kinetic in an Excel sheet, you would just run the model twice. Fast phase with the G value, slow phase with the 1 minus G mass, and just add up the concentrations at the end. So it's just that advantage of DFOP modeling, because you can combine rate constants and get the fast and slow phases. Okay. Some recommendations for modeling endpoints. Stepwise fitting is recommended. So this works by fitting your parent first without any reference to your metabolites. And then you keep the parameters of your parent compartment fixed, and you add your first metabolite, and then optimize your metabolite only parameters. And then you do a simultaneous fit where you optimize all of your parent and all of your first metabolite parameters. And then in a stepwise way, you keep on adding metabolites. Keep the parent and first metabolite fixed, add metabolite 2, optimize metabolite 2, optimize parent, first metabolite, second metabolite, etc. The parameter values at each step are used as the initial starting values, which we've talked quite a lot about. At each step, they're used as the initial values for the next step, and that improves the chances of reaching convergence and getting good optimized parameters. At the end of that stepwise fitting, and we'll take you through that stepwise fitting, it kind of happens naturally when you're doing it in Model Maker, because you'll fit your parent and then you'll add your metabolite compartment to it. Cake will also do it automatically, although I think in our workshop we'll take you through that stepwise as well in Cake. At the end, you should take all endpoints from the final pathway fit. And when I mean the final pathway fit is, however complicated your degradation scheme is, at the end you'll do one final optimization with all parameters. That's the final pathway fit. Of course, it's possible to fit your parent on its own, and sometimes when you add metabolites, you'll get small changes in the parameters for the parent. But ideally, you'll take all endpoints in that final pathway fit when you've optimized all the parameters together. If you do ever see large changes in parent parameters when you have added a metabolite, that might start to indicate that you've used an inadequate model. So if it has to really significantly change the parent degradation rate to optimize a metabolite, it might be because you've used the wrong model. Okay, that might be the wrong kinetic model or the wrong conceptual model. As I mentioned, be aware of cases where there's no decline phase described, because metabolite formation fraction and rate constant can be highly correlated. If your formation fraction optimizes to 1, again, that might be due to an inadequate parent model being used. And you might know from the data that you have that a formation fraction of 1 is extremely unlikely, because you know there are other metabolites that you know are going to be formed in sequence with, in parallel to the metabolite that you're really interested in. Okay, so you might know that you're not expecting a formation fraction of 1. In terms of goodness of fit, we use the same tool, so the typical plot and the plot of residuals. Just one extra thing to be aware of: systematic errors in your residuals might indicate that either the kinetic model is inappropriate, so you might have used an SFO model when you needed a default model, or it can indicate that your pathway is incorrect. Okay, so just that extra bit of complexity, not just that the kinetics might be wrong, you might actually have described your pathway incorrectly. Parent and metabolites with the highest measured levels will carry more weight than metabolites at lower levels. Okay, so for that reason, we don't calculate a single total goodness of fit. We don't calculate a single chi-squared value for our entire system. Each substance is evaluated separately. So we do a separate visual assessment, chi-squared, and t-test on each substance in our degradation scheme. Okay, otherwise it would be biased by probably the parent and the largest metabolites. And just there's no statistical test for formation fraction, but as I said, if it optimizes to 1 and you think that is conceptually incorrect, that might tell you that you've got the wrong model. Chi-squared test used for model comparison and for assessing individual goodness of fits of individual substances. Same indicative chi-squared value of 15%, but remember that's not an absolute cut-off criterion. Here, the t-test really can be particularly useful for metabolites that do not show a clear decline phase, because that can help you discriminate between metabolites that are really persistent and those that happen to be forming and degrading at the same rate at the end of your experimental period. So here is one of those examples that I showed you a few slides ago, where we had a metabolite with no clear decline phase, and here I've added the t-test result. And the t-test in that example is showing you that the fitted rate constant for the metabolite is not statistically different from 0. Okay, so the t-test has that particular useful application for metabolites that don't show a clear decline phase. I mentioned very briefly that there is some Biocides specific guidance on metabolites for terrestrial assessments, and we even discussed another version of it, or an adaptation of it, this week. So probably this will change a little bit as a result of the ARHI discussions. When was it? Yesterday. Okay, so tab entry M10 links to specific guidance that was developed on metabolites in the terrestrial compartment. I include the link there. So that really very usefully simplifies the soil assessment by recommending the use of the formation fraction in calculations. It's useful as a simplification because it then means you are using formation fraction for your PEC soil calculations and formation fraction for your groundwater assessments. Okay, so you're using the same consistent formation fraction in both. So you don't have that extra complexity of should I use a formation fraction or should I use peak occurrence. Okay. The guidance says, as a simple tier 1 approach, assume a formation fraction of 1, so basically assume 100% formation of the metabolite, and use a default DT50 of 1,000,000 days. Okay, so I mention it because already today I've been talking about what Focus thinks is a default DT50, and Focus says use 1,000 days, but just to really remind you that there is specific guidance that we've written on metabolites which uses that 1,000,000-day value as a conservative first tier. But that guidance goes on to say that those simple tier 1 approaches, if you run into a problem with your risk assessment, using those simpler approaches, then you can refine it by data from simultaneous kinetic fitting, so performing a kinetic assessment of your route of degradation study, to derive fitted parameters to refine the risk assessment. If you aren't able to derive reliable, robust parameters from that simultaneous kinetic fit, then you can refine DT50s using values from what we call the peak onwards. So in some of those figures that I showed you where there was a clear decline phase, you can just calculate much more simply the degradation or dissipation from the peak onwards, which will give you a conservative estimate of degradation. So like we call that either top-down or peak onwards. Or you might be able to refine this approach using data from separate metabolite dose studies. Okay. But the guidance says in those situations where you've got a DT50 from a separate metabolite dose study, keep the formation fraction to 1. That's right, isn't it? Yes. Trigger endpoints. Simple. Remember, the aim for selecting trigger endpoints is to find basically the best fit model that's not constrained to any particular kinetic model form. Okay, so you're not restricted like you are with modeling endpoints where you might want to accept an SFO fit. And it's more simple than you'd think, because the decisions that you've already taken on the best fit model for your parent should be consistently applied when you have subsequent metabolite fitting. Okay, so you've done some work already looking at best fit endpoints for a parent substance, and whatever decision you make on the best fit parent, you should consistently apply that kinetic model when you subsequently add your metabolites. Okay, so just use the parent best fit in your metabolite trigger fitting. As I said, SFO is usually sufficient to then subsequently describe metabolites, because the shape of your metabolite residue profile is a combination of formation and degradation phase. And the software tools do allow fitting of biphasic models to metabolite if you need to. Cake is limited to default for primary metabolites. Model Maker is as flexible as your own abilities will allow, so you can fit any kinetic model to any degradation scheme in Model Maker, but Cake is a little bit more limited. Last section, just because metabolites, as you will probably already have gathered, they start to get a little bit more complicated, so we often find ourselves in case-by-case options because of that complexity. Sometimes you'll find that the parent degradation rate and formation fractions are reliable, but your metabolite degradation is unreliable. So your metabolite degradation rate might fail that t-test, for example. So you can derive conservative estimates of metabolite degradation from fitting the decline curve from the peak onwards, that top-down approach, as recommended in the guidance link from M10 of the tab. Or you could try a conservative value, focus as 1,000 days if there's no decline, or try a conservative value and then re-optimize the formation fraction and check the visual fit, and I'll show you an example of that next. Alternatively, if you do have information from other studies, metabolite dose studies, then you can use this to fix degradation and just optimize the formation fraction. So focus there is actually quite consistent with those extra options from the Biocides specific guidance of M10. Focus also allows you to test alternative but conservative parameter combinations, but recommends that you always check visually to test conservatism. And the tools that we have allow you allow individual parameters to be fixed and remaining parameters to be optimized. So in Model Maker, where you have that little tick box to say which parameters do you want to optimize, if you want to keep a parameter fixed, set that parameter to the fixed value that you've chosen and make sure you deselect the optimization button. And that's just, it will just keep it fixed. And it's a very similar process in Cake, which we'll come to in workshop 3. Again, take care not to completely discard information on your metabolite, like metabolite DT50 values, simply because they fail the t-test. Remembering that the t-test tests if the rate constant is significantly different from 0. Just like parent, that can bias selection of endpoints in favor of those situations where degradation was faster. And where degradation is faster, it's more likely to pass the t-test. Okay? So it's often preferable to either test defaults in order to retain that information from those more persistent situations. But just remember that when using conservative defaults, be aware of the impact on subsequent metabolites. Okay. This is just an example of fixing a metabolite DT50. So on the left, we have our free-fitted optimized parameters. Okay, and the fits look pretty nice, but the metabolite DT50 in that case failed the t-test. Okay, so it's not statistically different from 0. So what we've done on the right is to fix the metabolite DT50 to our focus-defined conservative default of 1,000 days. We've kept that fixed and just re-optimized the other parameters. And the only thing that the model does mathematically is just slightly reduce the formation fraction. And you can see that visually the fits are almost the same. But at least we've now got a conservative DT50 that we've been able to retain rather than using this value that statistically is uncertain, I would say. Just a summary before we let you loose on Model Maker again. Remember that the conceptual model must reflect the actual degradation or dissipation pathway. If your conceptual model is wrong, it doesn't matter whether you're using Cake, Kingui, Model Maker. If that's wrong, it's just not going to fit to the data that you've got. Okay, so don't skip that step in a way. The formation fraction, this new parameter that we've introduced, that just determines the amount of precursor that is transformed into a metabolite. It's not the same as maximum observed, and think what you need for PEC modelling, although with the Biocides specific guidance at the moment we are following, you will pretty much always be using formation fraction in that case. But obviously the guidance was written for pesticides, and so there's extra complexities there that we don't need to worry about. Remember the importance of visual assessment and those special considerations when there's no decline phase. So think about the importance of the t-test to test whether that metabolite rate constant is significantly different from 0. And remember that metabolite formation fraction and rate constant can be highly correlated, and that's particularly an issue, again, where you've got no decline phase. Modelling endpoints, good description of your parent precursor, at least up to 10%, because that covers 90% of the formation of the metabolite. If you need a biphasic parent, I would say use DFOT because of the advantages of being able to combine endpoints and have those fast and slow phases. For trigger endpoints, use your parent best fit model. The added complexity means there's plenty of case-by-case options for you to use. Top-down modelling of the decline phase, conservative DT50s, 1,000 days, million days, refit the formation fraction, fixed values from other studies, metabolite dose studies, for example. And just a reminder that when using conservative defaults for parent or intermediate metabolites, be aware of the impact on any subsequent